Aloha and welcome to our presentation on a transient classification system for the Open Power Quality Project. My name is Philip Johnson. I'm a professor at the University of Hawaii at Manoa in beautiful Honolulu, Hawaii. And I'm here with Anthony and Charles, my co-authors. We wish we could be there with you in beautiful Athens, Greece. But our schedule didn't allow us to attend this year. So we're really sorry about it, but we're hoping that you can watch this YouTube video and learn a little bit about our system. I'm going to start off and kind of kick things off, and then both Charles and Anthony will talk for parts of the presentation. So the idea behind the Open Power Quality Project and what led us to this work on transient detection is that with the rise of distributed intermittent renewables and their incorporation in the grid, particularly in Hawaii in a smaller grid, there is the possibility of new kinds of power quality problems that the grid isn't architecturally designed to deal with when generation is bottom up rather than top down. So we'd like to have some way to better understand if power quality problems are occurring and classify them in ways that can help folks in the grid to understand how the incorporation of distributed intermittent renewables are impacting on the grid and hopefully lead to ways that we can have more and more renewable energy in the grid. So that's the essential idea of the Open Power Quality Project. What we did is we built little hardware devices that are relatively cheap, under $100, and you can plug them into wall outlets and they measure frequency, voltage, and total harmonic distortion, send that information to the cloud in a fairly sophisticated way that enables us to detect potentially interesting events in the grid and request the high fidelity waveform from these little boxes. They're holding waveforms in a buffer for a little while until the cloud decides that it's something that would be of interest. So once we have these waveforms, we can do things like look for transients, and that's the subject of this particular work that we're talking about today. So what I'm going to do at this point is turn it over to Charles, who will talk more about transients and the kinds of detection algorithms that we used.
Okay, thank you, Philip. So a transient is a short-lived disruption in the nominal waveform of the system. And our algorithm can classify 4 different types of transients. And these transients are defined in the 1159 IEEE standards. The 4 different types of transients we can classify are impulsive, arcing, oscillatory, and periodic notching. And we will cover each of these in later slides. The first step to our algorithm is signal decomposition. We need to extract from the raw waveform the fundamental waveform and the potential transient waveform. In the figure on the right-hand side of this slide, we can see in the top plot the raw waveform that we might measure at one of the open power quality boxes. And in the bottom 2 plots, on the left-hand side, we see the fundamental waveform that we would extract, and on the right-hand side, the transient waveform. This specific example is an oscillatory transient. The way we extract the fundamental waveform is with a digital implementation of a 4th order low-pass Butterworth filter. We extract the fundamental waveform and then subtract it from the raw waveform to get the potential transient waveforms. The next step of the algorithm is feature extraction. In our practical implementation, we wanted to avoid as much computational work as possible, so we extract power quality features sequentially and rule out different transients as much as we can. The features we extract are shown below. We extract whether or not the transient's unidirectional, the number of zero crossings, the zero crossing periods, whether or not the signal could be fitted to a sinusoid, and whether or not the signal is periodic. The last 2 features are the most interesting, and we will cover those. So to determine whether or not the signal could be fit to a sinusoid or not, to determine whether or not the signal could be oscillatory, we perform an incremental f-test on a least squares least squares regression to the complete model shown in this slide. The reduced model is shown in the bottom equation, and the incremental f-test will give us a statistical significance of the fitting, and we can define a threshold of how statistically significant we need the fitting to be to determine whether or not the signal is truly sinusoidal or not. Next, periodicity. We use an autocorrelation technique. The signal is autocorrelated, and once that happens, the resulting signal has peaks at the same periods as at the same periodicity as the original signal. We can define a height threshold to determine whether or not the signal is truly periodic or not. You can see more details of this in our paper. The results were promising. A simulated periodic notching transient is shown in this slide in the top plot. A periodic notching transient is a periodic and strictly negative in power transient. So we can see in this slide the extracted transient waveform has negative voltage measurements at the positive quarter cycle of the raw waveform, and positive voltage measurements in the negative quarter cycle of the sinusoid. And this tells us that it's strictly negative in power. And next is the impulsive transient. This is an example of an impulsive transient, and an impulsive transient is a impulse. It could be positive or negative in power, and then a decay. An arcing transient. An arcing transient is a bipolar and random in frequency. Bipolar meaning it could be positive or negative power disruption, and random in frequency, and we can see that in the extracted transient waveform plot in the bottom right hand side. Next is a multiple zero crossing transient, and this is a feature that could be added on as meta information for each of the 4 different types of transients we classified, in addition to other features such as like the peak voltage and the frequency of the transient. So we focus our attention to the zero crossings in the fundamental waveform and determine whether or not additional zero crossings are caused by the transient. And lastly, I'll pass it off to Anthony for some conclusions.
Thank you, Charles. Since we've seen such promising results using simulated data, we're now taking this algorithm and deploying it in a real distributed power quality network. We're aggressively deploying sensors across the power grid at the University of Hawaii at Manoa campus to study how power quality propagates over power grids. And this transient detection is only one part of a suite of power quality phenomena that we're measuring. We're also looking at different types of voltage, frequency, and total harmonic distortion phenomena as well. We're also working on implementing predictive models so that we can forecast power quality problems using previous power quality problems as a predictive model. You can find more results and more information online at openpowerquality.org. We want to thank you for your time, and we look forward to your questions. Thank you very much.
Okay, thanks a lot for listening to this, and our email addresses are listed in the paper, so feel free to send us an email if you have any questions. And take care, and we hope to see you next year at NRD.
Thank you very much, and have a good time at the rest of the conference.